Yeah. Thank you, everyone. Thank you, everyone, for joining in. Today, we have Professor Guerrero talking about DC microgrids. Professor leads the Center for Research on Microgrids in Aalborg University, Denmark. I thank Prof for agreeing to give this talk. So please go ahead, Prof. Please go ahead.
Yeah, thank you. Thank you very much for this opportunity. I also want to say hello to a lot of people here. Hello, Shethan. You are always here in these talks, and also some of our good PhD students, Luana, or even Umer. So also thank you for all of you being here. You know that our center is dealing with many different aspects on microgrids, but today I'm going to just let's say focus on DC microgrids. First of all, this is something how I like to start my talks. Please don't believe a word what I'm going to present here. You should try to verify everything. It should be a lot of things that is just my personal, let's say, opinion, or even some data that could be wrong. So this is kind of a disclaimer. Yeah, and I will say that this is something that you should take also in advance. So don't trust what I'm saying here, but also don't trust what we are, for instance, publishing, because it will be a lot of errors as well, or what you see in internet. Yeah. So whatever you in your life, whatever you want to know, just first verify it. That's also a scientific approach, I will say. Yeah. So this is something about me. Active ecologist from teenagers, from 10 years old. I started with electronics, and then after this studied telecommunications. This is what drives me, telecoms. So everything about radio communications was really from the very beginning my passion. And of course, always I try to mix with the other passion I have, which is music. And there's also a lot of electronics ongoing there. This is also one of the products that I developed during my PhD. Right now, it's a product in the market, finally, after a lot of troubles. It's a UPS system with modular capabilities, and many of the concepts that maybe you know, like Droop controllers or virtual impedances, are there embedded. So I'm very happy that to contribute on the society. And this is our team members from our center. We have around 50 people here, and this presentation is also part of their, let's say, work. So it's not something that I'm doing myself, as maybe at the beginning, but this is also kind of a teamwork. This is some pictures from our facilities. You can see here that in our tables, it's only a computer, maybe a mushroom button, and let's say electronic systems inside. So safety, it's very important here. So no cables in everywhere. So everything is, let's say, embedded inside our setups. Our setups are well connected, and everything is grounded. So this way, if there's some problem, automatically we have the protection system locally and let's say also globally. So that's also something very important, to don't be in rush once you are, let's say, trying things. No coffees, no teas, no whatever, right? So again, we have also safety rules, very strict in our lab, but at the same time, we have the good thing that from MATLAB Simulink, we come with some ideas, we just compile it, and we use several hardware in the loop tools to develop our control systems and to check everything. Sometimes we need to make hardware modifications, and this, of course, means that we do it in a separate workshop, and then we come back and then we test everything. I know that for some people this is a waste of time, but I will say that this is very, very important for our safety. Yeah, especially when we try to work on things like 400 volt in 3-phase, and then, as I will explain here, in high voltage, like, well, close to medium voltage, because we talk about up to 1000 volt in DC. Another important thing of our concept here is that we are embedding hardware systems. So it's not exactly a hardware in the loop, but we use real hardware However, all about, let's say, solar, wind, battery systems, and loads are emulated inside our DSP system. So let's say that everything electric is real, but let's say that the prime movers are virtual. Also, another important thing of our lab, and this is something that we are going to close very soon in one of our projects, is multi-microgrid systems. We are doing this for companies like Huawei, and what we are testing is how multiple microgrid systems can be interoperate for some areas. Especially in our project, we have been developing multi-microgrid system for a rural electrification. This is part of our facilities. Not only we have these labs, but also we have a demonstration house. And this demonstration house can also emulate AC and DC distribution. I have more slides, but because of lack of time, I don't have more here. Not only trying to also make research and development in our facilities together with our industry, but also I try to become a customer, so finally a prosumer. I install some PV panels also at home, and of course my car is electric, and I install also my own electric vehicle charging station. Yeah, so this is something that I live from my morning till night. It's kind of, if you ask, for instance, to a lion how you can separate your professional life or your personal life, lion will tell you, I'm just resting and sometimes go to hunt because I'm hungry. So like a doctor taking your own pills, everyone knows right now that I'm a fan of Dr. House. And you can see that in his TV series, 90% of the time, the illness is lupus. In our case, when you try to address control of power electronic systems, 99% of the cases is always solved by using PI control. Maybe some modifications, but just PI control. So this is something that made me think that really we need to go to another direction. So this is an important sentence also from Dr. House. If you really want to do something, always, I will say always, you will find a way. Otherwise, you will find always the excuse. So if you want to do something, do it. That's my message. Yeah. And then another important thing is that we all talk right now today about artificial intelligence, but still, I wonder if we know how our brain works. And this is something that, if you know me, you know that I'm really excited about this idea of having 3 brains. So the 3 brains, you can see, we have our mind, then we have the heart, and we have the gut. Discoveries knows that we have around 18,000 million of neurons in our mind. And then in the heart, we have 40,000 neurons, while in the gut, all the part, let's say, of digestion system, we have 500 million neurons. So the same as you have in a cat's brain. Yeah, that's why there's right now a lot of studies regarding bacteria that you could have in your intestines, how influence your behaviors. And right now we are talking about science now. So now we understand also another important thing that before we didn't know. Maybe you hear that we are using 5 or 10% of our brains. This is basically wrong. Today we know that we use 100% of our brains, so be relaxed about that. However, we just can use simultaneously 2% of these neural networks, and this is because of glucose and oxygen limitations. So it's like blinking, you know, different parts of our brain. However, we normally use similar neural network paths, and that's why sometimes it's difficult to change. Nevertheless, even if you can feel that it's difficult to change, neuroplasticity also demonstrates that we can still change our physical structure of the brain by changing our thoughts. So that's very interesting because that means that energy make changes over the matter, right? And of course, about reality. talking also about three, this is always three, you know, when we talk about the three layers of control, and here we talk also about the brain that you have, let's say inside your head. We have also here three brains inside. We have first the reptilian brain, which have 500 million years, which is more, you know, like action reaction, also always trying to find opportunities, yeah, find opportunities and action reaction. The next brain has been developed 200 million years after, and this is the limbic brain, which is the one who have the mammals, and this is emotional and having feelings, yeah. So that's why you can, for instance, you can give love to your dog, and the dog will give you love back. But don't try to give love to a snake. It's really useless, yeah? Then we go a little bit farther, and we have the neocortex, which is just from human beings, and this has been developed only 100,000 years after. That's why you can see here, let's say the weight. We have 200 million years of limbic brains, emotions, and then we only have 100,000 years of neocortex, which is rationality. That's why our decisions are always based on emotions. Even if we feel that is rational, the rational part only gives the justification. And now you observe yourself during the day and you will tell me if it is true or not. Another important thing is about stress. It has been also demonstrated for many years that stress is good if we increase the stress until, let's say, up to an optimum activity. However, if we increase still the stress more, we arrive to what is called de-stress and also arrive to anxiety, panic, anger, etc. So the syndrome of burnout. That's why it's very important also to keep the stress levels in a good level. Yeah. Talking also about trust and fear. It was last year that has been discovered that 3 parts of our brain are the ones who are, let's say, in charge to have fear or to have trust. These 3 parts are the same. So that means that the areas to feel trust or the areas to feel fear are exactly the same. That's why it's not possible to feel trust and fear at the same time. Yeah, or you trust or you fear. That's very important, right? So now other important things also about the empathy system. We have logic empathy and we have also emotional empathy. Emotional empathy, for instance, is more connected to the mirror neuron systems. So this has been also connected to the research done by another researcher that has been demonstrated how we have some mirror neurons that once we see, for instance, someone suffering, we suffer at the same time. So because of that, they give her the Nobel Prize. And this emotional empathy, all of we have, maybe women have a little bit more, let's say, while logic empathy, it's more for the men. You kind of understand the situation of this person and then you feel the same, let's say, feeling. Yeah. Other important things, our heart. Our heart, as I explained before, we have 40,000 neurons in. Yeah, so that's very important. Yeah, you can see how our heart is also generating hormones. This is something that in the past we didn't know, but nowadays we know it's like this. And we are generating from the heart amitriptyline, which is for controlling stress neurons. And also we generate oxytocin. Oxytocin is what we generate when we feel love, trust, and fidelity, and it comes from the heart. So now it's not strange for us why we are using the language. When we say, I'm saying this to you from the heart, it's really like that, you know? So oxytocin is the same hormone that, for instance, a woman generates when they are waiting for a baby. Exactly the same, right? And recent studies has been shown how a lot of communication is coming from the heart to the brain, much more from the heart to the brain than from the brain to the heart. And now I ask you, who's the boss here? Some studies from the HeartMath Institute, in Germany, show how our heart rate is changing, and this is normal. Our heart rate is changing all the time to maintain the blood pressure constant. Yeah, if you know something about control, you can understand this. Now, if you have feelings of frustration, anxiety, worry, irritation, you can see the waveform you have. While if you feel positive emotions, appreciation, love, coherence, you can see almost a pure sinusoidal. Yeah. So I will say that this is amazing. We can measure that things. We can measure that things, and we can see how our heart can be synchronized with the brain. Yeah. And we can do this. We can measure this by measuring heart rate, heart beats, and also brain waveforms. I will say that this is really amazing. We have been also measured the heart electromagnetic field, which is 5,000 times bigger than that in the brain and can be measured up to 3 meters. Indeed, you know, having a choral, many people singing at the same time, it has been discovered that their hearts has been synchronized. There is a study from this year that demonstrates this also. That's something very, I will say, very amazing. Also some other tests, like using a boy and a dog. Once they are in the same room without touching each other, you can see how they can enter in coherence once the dog expresses feelings of love towards the boy and vice versa. Both hearts enter in coherence. Once the boy leaves the room, they are again in uncoherence. I will say that this is a very good finding from the HeartMath Institute. So you can see a lot of people is fighting the wall, and I will say focus on yourself, because it's where is the key point. And I will say that something like this happen also with energy. That's why my passion is inside microgrid systems. You can see some examples. Everybody knows that I like this example. This example comes from Japan in Sentai. Yeah, Sentai was a demonstration site in 2004, and they finished in 2007, founded by Inedo. And it is supporting the hospital there and also the communication system. It can support 1 megawatt. So it's really a very powerful microgrid. Basically, solar panels, a fuel cell, and a number of diesel generators. This is the electric extractor. It's really like a DC microgrid if you look, because the core is a DC bus of 430 volt, then a battery system, and then a number of DC-DC and AC-DC converters there to support DC loads and AC loads. You have to think that in communication, we have a lot of electronic equipment that is supporting DC. Now, these are some pictures from Fukushima disaster, because Fukushima is very, very close to Sentai. It was terrible. Now, 9 years ago, we don't forget this. We don't forget this because it's not only about the disaster, natural disaster. It's also the disaster that caused nuclear power plants. This is something that we cannot forget for the future. You see, during 3 days, this microgrid system was operating in Ireland. 3 days supporting the hospital. 3 days helping people to call to their families. Yeah. So clean technology supporting a disaster that was even worse due to other technologies. Yeah. Sometimes it's important to bear in mind that behind technologies, there are also ideas. That's why we also work, let's say, on having more resilient systems. Thinking on resiliency is here very, very important, right? Because we have to think on how we are going to restore, and in the case of, let's say, Sentai is very clear, to restore the recovery action So we know that from the beginning, maybe we reduce the performances, and then we had to have a strategy to restore the energy system. Maybe not 200% as before, but enough to survive those days of outage. Yeah. So basically what you see here, detection of the disaster and then mitigation. That's what also we call resiliency. This is another example that I like always to talk. It was an example of increasing efficiency by reducing the number of stages. This was for a data center. Normally, we have a lot of data centers moving to DC. And you can see here that in this data center, we need a number of voltages. And then normally when you go off the shelf, you just go and try to find a UPS system. In that case, it's an online UPS system to support the front end. While removing, let's say, the UPS system by just a rectifier, putting here the battery systems, and then using a single DC-DC converter, the efficiency has been increased, let's say, 11% at a minimum. So between 11 till 14%, which is kind of nice. And in this project has been demonstrated that this is cool. And also we can regulate the voltage, the intermediate voltage, because this voltage is connected to a number of point of load converters. So that means that voltage can be adjusted according to the load. This is just one example from Intel. They build the same infrastructure for AC and for DC. And to support, let's say, a data center. And in that case, they built exactly the same, kind of the same equipment, but adapted for both, let's say, possibilities. And they just found 7% of improved efficiency for that case, and 6% of savings if you move to DC. So the conclusion is, if you have to make it new, it's good to have a DC data center. If you have to retrofit, it's really difficult to justify it in terms of economy. All right, let's talk about control on DC microgrids. If we have a number of converters, imagine that you have a grid interface converter, you could use kind of a Droop controller. And then we can have, for instance, a number of, let's say, solar converters or wind converters. They can work on Droop mode, let's say, if let's say the power is enough. So this is regulated by the level of voltage, but we can move from Droop mode to constant power, let's say to the maximum point power tracker, depending on which is the voltage level. That means that if the voltage is a little bit lower, then we can work on MPPT. However, if the voltage raises a lot, this means that we have a lot of generation, so that we change it to a voltage source. Yeah, and this voltage source, if we want all of them to share, then we have the conventional Droop control. So that's very interesting because here we have a curve, which is basically a combination of a Droop and an MPPT. The same ideas of Droop control has been applied also for small converters, like, for instance, let's say point of load converters or voltage module regulators, EMRs, which are, for instance, supplying microcontrollers or microprocessors. You have to know that in a microcontroller or microprocessor, you have very high current to supply and very low voltage. But you have huge, let's say, changes in current. So your microcontroller maybe is sleeping in the sleep mode, and then you wake up, so you can have sleep rates of several, let's say, kiloamps per microsecond. And this is really something huge that you have, for instance, in CPUs of computers. And if you try to maintain the voltage very steadily, then once the current goes down, once the current goes up, the voltage will go down, and then you go back with your integrator. And once the current goes down again, for instance, back to sleep mode, then the voltage will make a spike and go back again. So this is because your system is very, let's say, nervous, always trying to correct and having exactly the same voltage. I'm saying here that if we try to maintain the voltage inside the tolerance band, these spikes disappear. You have to think that these spikes can kill the CMOS of your microcontrollers immediately, because in the gate you produce a huge voltage change, which will produce a huge voltage spike that will break, let's say, the layer that you have between the drain and the substrate. So normally you have like oxide of silicon, and this will be just a short circuit. So this is one of the things also that Droop Control can help us, not only to share power, but also to help transient response in our systems. When we think about sharing a number of, let's say, DC-DC converters or AC-DC converters forming DC microgrids, we can use Droop controllers in some of them, the ones who they want to control the voltage. But then if we want to restore the voltage, we can use something that we call secondary control. So basically, primary control is based on the Droop control, which is also called virtual impedance, virtual resistance also, when it's a resistance, Droop control, adaptive voltage positioning. All these names are basically the same, right? So finally here what we do is we can make a restoration by using a controller. I'm putting here a PI to make it easier, but it can be whatever you want, depending on the specifications. And then in the top of that, sometimes we build what we call also Treasury Control, which sometimes is an energy management system. But in that case, this energy management system can be connected to another control loop, which is to control the power flowing between the DC distribution system and the DC microgrid. This is especially interesting when you have a number of microgrid systems and you want to share the power between them. So here you have the example of the simulations that we did a lot of years ago. Yeah, the same year, by the way, the same year of Fukushima disaster. It was basically two DC-DC converters sharing the load, using Droop control, fixing 400 volt. You can see once we start the Droop control, the voltage goes down. If we increase the load, the voltage still goes down again. Even the power sharing is well achieved. What happened when we start the secondary control, we restore the voltage levels. And then if we start the tertiary control, we are also able to, for instance, import power from the DC distribution grid. In that case, we imported 20 volt. And of course, you do that by decreasing the voltage level inside your grid. So I think that with this very simple test, we demonstrate that DC microgrids could have a lot of potential. And I know that from that time, a lot of people start working also on DC microgrids because it's something that is coming tremendously. Here you have some examples. I want to go to some examples because it was a lot of promises that homes can work on DC. And this is true technically, however, there's a lot of problems there. Yeah, I just share a very funny video from YouTube talking about DC at home. I can also share with all of you. But I will say that here what is happening is that you need basically a huge rectifier in the input of your house. And this rectifier will always work outside the optimum operation point. And that's why you can see that it's not happening. However, you can see a lot of places in which there is this possibility. One of them is, for instance, right now a project we are starting with Madagascar with a number of what we call nanogrids in the level of hundreds of watt, very small power houses, in which then it makes sense to go in this direction. But we cannot see happening, for instance, here in Europe right now. You can see also at the same time how other companies, this is just one example from Schneider Electric, they try to also come with some ideas. In that case, is promoted this product for India. to put, let's say, photovoltaic systems that could be also connected to smart meters in DC, having 230 volt on DC for distribution in distances of 1 kilometer, 2 kilometers, let's say. So here we are also talking about, let's say, DC nanogrids almost, let's say. All right, one of the main ideas was also developed by one of my good friends, Hiroaki Kakigano, and he developed this nice idea, which I identify and propose him to write this paper for the transactions on power electronics in a very timely matter. So he was also here in Aalborg, and I think that this view of having bipolar DC microgrids is really good. So we are going to have like a three-phase system, but thinking on DC. You have the neutral, you have positive, and you have negative. He developed this for potential DC microgrids at home in Japan. However, even if it was not successful, right now there are some installations, for instance, in Finland, that they are using it for distribution in the level of plus minus 750 volt in ranges of, let's say, houses, distributed houses, AC houses, but with DC distribution. So this is happening in several areas, which we need also resiliency. For instance, one of the phases can go down and still have the other phase working. And it's very easy also to generate, if we need a single phase AC, because just with a half bridge, it's easy to generate the let's say, the waveform that we need. One of the also ideas that came in Europe was with the company REBus, and the company REBus developed DC microgrid systems. However, they entered in bankruptcy, but right now it became a standard. And this standard is really nice because it's kind of using the DC concept in red and the AC concept in dark, in blue, sorry, in black. And then you can see here, for instance, the number of renewable energy systems that we have, in which they can work on MPPT, but however, if the voltage raises, we can just reduce it. This is exactly the same concept that we have in AC grids, playing with frequency. You know that in an AC grid, if the frequency increases, means that we have a lot of generation. So here we have the same idea, but when we have a lot of generation, the voltages start to raise, and then we have to do something. And do something means that we can reduce the power generated by your sources, so taking them out from the MPPT, let's say, operation. The other thing is what happens when we don't have enough power or energy here in the generation side. Then we can also create what we call also load shedding. So starting to disconnect the loads also. I think that the concept is very cool and nice. And also in the top of that, they develop also some FSK modulation and communication, let's say, based on DC power line communications. But the control scheme was just based on the DC concept, DC control concept, right? So just looking at the voltage and taking actions, everyone locally. Yeah, so thanks to that, also we start a project. Also, Professor Kakigano was also involved in this project. And it was basically our center together with Japan and Virginia Tech, also in the United States, that we developed the schemes that what we call the future residential low voltage DC power distribution architectures. And it's basically having a 380 volt on DC for distribution, and then going down to 48 and 24 volt for different loads, let's say. Yeah. Even if it was a lot of promises to go in, let's say, in home applications, I can see that these things are shifting to other areas. Yeah. For instance, electric vehicles. It's kind of interesting to see how in our homes, for instance, this is one picture from my Nissan Leaf, we can charge the car from AC or from DC. If it comes from AC, you have a rectifier inside, and then you have your battery inside. So basically, your charger is really on board. However, when you try to charge it, let's say in DC, this basically for fast chargers, and we have, for instance, the standard of CHAdeMO. So here you have just a positive and a negative plug, and those other plugs are for communication. Yeah. And the other interesting thing, what is happening is you can see that some products like bidirectional converters are coming also at home. And this is very interesting right now because we pass and we will pass a lot of time working at home. So it's not like before. And I can tell you there is no coming back. You start to know that. So that means that users of electric vehicles start to think to having bidirectional converters to use the solar production. So you can use it also during the night. And it makes a lot of sense, at least for me, because I have 6 kilowatt available power in peak when the sun is not there anymore. So I will say that this is very interesting, and there is a market coming here. Another interesting amalgam of things, no? People like me that have solar panels in the roof with conventional inverters, they can merge also together with hybrid inverters that can be connected with solar PV and also stationary batteries, not only electric vehicles. And I will say that this is a very nice combination. We did a project also talking about DC. It was a European project with the Commune of Oslo to develop also DC microgrid systems. It was also Zagreb inside. And what we developed is the concept of having stationary energy storage systems for support electric vehicle charging stations. We want to also extend this in the future for ports to charge ships, electric ships. And here in that case, we use flywheels to support it, but also second life batteries can be a very good option. Talking about electric vehicles is not only talking about electric cars. There are many other vehicles, let's say. And if we take a look on, for instance, the Boeing 787, which is a more electric aircraft, they are coming here. I don't think that the main engine is electric. Still, we are not in this point, but they are auxiliary support systems that are supporting the engines and having it more efficient. And it's really a huge amount of microgrids. So this AC microgrids in red, and you can see in green DC microgrids. Bipolar DC microgrids, as Professor Kakigano was proposing for homes, in this case in the level of plus minus 270 volt. So that's, I think, a very nice thing that is happening also, how DC microgrids are penetrating also, let's say, aircraft applications. And the other is, of course, ships. So we know that these ships are coming more and more with electrification and also hybridization. So it's happening something a little bit similar like in cars. They come now hybrid, and some of them go into full electric. So yes, if you take a look, for instance, on a DC microgrid for a ship, you have a number of diesel generators, and then we can have, for instance, a number of rectifiers, so AC to DC converters, and then we have 2 buses. This is for redundancy, because if some short circuit or overload happen here, we can open this breaker and still the other bus will work. And then we have a number of propellers, so basically motors, supplied by inverters with variable frequency. So this inverters with fixed frequency for supporting the loads in the ship, the AC loads. And then all these motors are with variable frequency because you have to change according to the mission of the ship, how will be the speed. You can see this is just one example from Siemens, in which they implement DC microgrids, and it's already it's already a product. This is the blue drive plus C. And you can see here also the batteries also embedded, power electronic systems, and propellers. I will say that this is an amazing product. And then, of course, ABB comes with another idea. It's the same DC microgrid system, but in that case, in order to reduce losses, the converters are embedded with the motors. So if they are close each other in the same box. And the good thing of that is that you reduce the distribution losses. However, you can see that the DC connections are still, let's say, far away. So you don't have a box anymore. You have long lines. And this means that you have to increase a lot the voltage. And if you increase the voltage, of course, you can imagine that protections become more difficult in DC. So this is one of the drawbacks, let's say, when we go to DC. We go to DC, we have more efficiency, but if voltage have to increase because the power is increasing more and more in those ships that needs more powerful propulsion, then we pay with the problem of course, protections. And maybe you say, don't worry, I have something in my lab that works. When we talk about maritime industry, things has to be tested for at least 20 years. We are not playing. We have people inside, and it's very complicated situation. Yeah. So you can see here the variable frequency drives, which are placed close to the propellers in that case. Yeah, and the long cables that you could have from, let's say, the converters to those places. Yeah, and now it comes why we are using DC in ships instead of AC. Well, we have still a lot of AC ships, but some of them are shifting to DC. And this is because if you go to AC, you will fix the frequency here at 50 or 60 hertz, depending on the country. So if you take a look on the characteristics of a generator, the losses, which are converted to CO2 emissions finally, are having here an optimum, a minimum optimum for certain operation point. So this means that if my power is going here, I will have here the optimum for a certain frequency. If the frequency is this second one, then the optimum will be here. This is another frequency, the optimum will be there. So this is basically fixing where is our optimum point. However, if we use DC microgrid systems in ships, we just have a rectifier, and then we have just an inverter here. So that means that we will fix the voltage, and the speed of the synchronous generator will be decided according to how much is the power. So that means that if we are here, we will decide to take this frequency. If we are here, we can decide to take this, and so on and so forth. So we can adjust the speed of the synchronous generator according to how much is the power. So that means that in that particular case, we will achieve better efficiency. It's not for everything DC is better than AC. I cannot agree with that. In this particular case, it's like that because of the independence of frequency of the synchronous generator. Yes. Here you have one example of a project we did with Taiwan, and this is the Happiness Ferry. So this ferry was in the area of Kaohsiung. So you can see here, it's connecting Kaohsiung with an island. And this was 4,500 passengers every day. So yeah, this was really polluted, this area. So what we did is we take out all the old, let's say, engines, all out. And we start from scratch. We put power electronics inside, yeah? So, and we used, in that case, Vicedo products. These power converters right now are from Danfoss. So Danfoss just took over Vicedo. And you can see here the scheme. We had a couple of diesel generators. The rectifier, it was just a 3-leg converter, 3-phase converter, bidirectional, yeah? So in that case, the power was coming from here to there. And here was our DC microgrid system, 750 volt DC, to supply battery system. In that case, the DC-DC converter was exactly the same inverter we use here. However, it was like 3 buck converters interleaved between them and interconnected, right, to reduce the ripple. Power stage is the same, but you know, it's kind of much easier if we just use the same topology for each of them. And here you have exactly the same topology. It's a 3-leg converter, so from AC to DC, variable speed. So that was the result. It was the first Asia hybrid electric ferry. Yeah, so we are very proud of that. And here you can see this is an electric motor, as many people have in their labs, and battery system. Those batteries are not whatever batteries. These are Super B batteries, which is from Holland, and they have the stamp to go on a ship. So you cannot put whatever you want. You need the stamp to go offshore or for maritime application. And much more ships are coming now with this collaboration with Taiwan. And because of we have more electric ships, and some ships are coming also to the port, polluting a lot the area because they need electricity. For instance, if they come with a lot of fish, they need electricity for the freezers. And the electricity, if it's not provided by the port, they will start the diesel generators, polluting the area. Right now, this is less and less accepted, especially in the north countries of Europe. So what we call ironing devices are coming. So basically, a station, medium voltage station with converters, and then a connection to the main circuit, main power system of the ship. Yeah, you can see here, this is one example from Rotterdam port, and we have the same idea to reproduce here in the port of Aalborg. So I will say that this is coming very strongly. We don't know if DC cold ironing is coming still, but we have, for the case of ferries, this possibility. So it's really coming for certain kind of ships. You can see here in this figure, by the way, made by Luana, my student, hello, that this, we could have the DC-DC converter embedded inside the ship in some cases, or you could have also the charger in the port. This is changing a lot. I will say that, for instance, when we talk about ferries, normally you have on board the charging, let's say the charger. However, in some other cases, it's discussed to have it outside. So this is something not clear, but I will say that that is coming right now. Another important thing, when we talk about AC cold ironing, you think, okay, I'm supporting an AC ship with different voltages and maybe different frequencies depending on where it's coming from the ship. But however, it's very important to have your own inverter to select voltage and frequency. And then it makes a lot of sense to have a DC microgrid in the level of medium voltage to distribute the power between the inverters that will be connected to the ships. And that's very important to do it like this. And there is a second reason to use the inverter in the port. And it's because if you have the inverter in the port, you're able to synchronize with the ship. Otherwise, you will have huge spikes because you have no inertia in that case in the port, but you have inertia if you have diesel generators in the ship. So it has been demonstrated, and this is a study in Poland, that huge currents can come when you try to make this kind of cold ironing if it's the ship who has to be connected. So thanks to that, you need to have the inverter in the port side, and then you need to have this kind of DC distribution system or DC microgrid in the port. Something else that is coming also, port cranes. Yeah, port cranes also needs to be electrified. We have still a lot of cranes that not only use diesel, but they use diesel because they need electricity. So they need a diesel generator, and they embedded inside the port a diesel generator to generate the electricity needed for the crane. Yeah, it's a little bit crazy if we think it like that. So right now the idea is to remove all these diesel generators and to have also an electrical distribution system in the port. And this makes a lot of sense, because if you think that you have a ship that coming with a lot of containers, when we flip up this container, we need to put energy. However, when this container has to lift down, then your motor start to work like a generator and then start to generate power. Today, this power is burned in dummy resistors, so we are just wasting this power. If we are able to create DC microgrids to regenerate the power, put it in batteries, put it in supercaps or other devices, we could reuse this electricity again, or it could be also be used by other devices in the port or in the ship. And according to different studies, not only this, we also made another study. All of these studies demonstrate that we can recover between 40 and 50% of energy, and this is huge. And at the same time, we can reduce also the power needed in the input, let's say the power needed by the port as input. So that's also very important. So we reduce the power peak needed there. Yeah, that's all from my presentation. Thank you very much. And I want to finish with this sentence from Thomas Edison, also a fan, let's say, of DC. Genius is 1% inspiration and 99% perspiration. Thank you very much.
Thank you, Prof. Very good presentation. Thank you very much for the detailed talk. Can we take quick questions, Prof, from the audience? Quick questions.
Yeah.
Bijit Day, please unmute yourself and go ahead with the question. Bijit.
Hello.
Yeah. Please go ahead, Bijit.
Yes, sir. My question was, there was one slide on bidirectional residential microgrid that you showed. So in that there was something called a voltage balancer. So I didn't quite get what was going on with that.
Sorry, maybe I can try to recover the.
Yeah, or voltage balancer function.
Yeah, I think that you mentioned about the bipolar DC microgrid system.
Yes,
right?
sir. Yes, sir.
So in that case, yeah, I want to go back here. I believe that it's like that. So in that case, what you can do is, if you see that the voltages start to be unbalanced, you can just inject some current in some of the levels of, let's say, one of the two levels, so that you can compensate the voltage from one side to the other. So it's like a power converter in the middle. Yeah. So you can imagine that you have here in one side, all these converters are just one phase, so from 0 to positive. And this voltage balancer, what it's doing is, it has an input of two phases and convert it to two phases. So it just, you can imagine that it's kind of a capacitor plus a converter based. So just switches and capacitors, and then you can balance it. It's just a power converter.
Okay, to hold the DC bus stiff, Prof, that is the function?
Exactly.
Okay. Bijit, you had one more question about point of load. Go ahead.
Yes, sir. You have showed some, I forgot the number of the slide, but there was something called point of load converter. So where in a microgrid can I expect to encounter one such converter?
Yeah, that's a very good question. Sometimes you can find the name of point of load converter, and in the past it was more voltage regulation modules. Voltage regulation modules are DC-DC converters that has been used for supplying computers and electronic loads. And when you think about point of load, it's kind of a voltage regulation module, but more generic. So point of load converter can be a converter which is very close or embedded with the load. For instance, if you have an LED, the LED normally have an embedded converter. They are together, you know, just, you don't have lines in the middle. I don't know if
Okay.
you catch my point. So you have
They are,
normally box, in which you have
there's no
the
power.
LED and you have the converter. There is no lines to the load.
Okay, okay. Yeah.
Okay, sir.
Yeah, Bijit had one last question related to recovery time frame of recovery for microgrid system.
Yes, sir. You showed in one slide there was there is a definite there is a targeted time in which you can recover, and then what we can get from microgrids. So I'm saying, what exactly is the quantification of that?
Sorry, can you again?
So Bijit is asking, there was a slide where you showed recovery of a microgrid, but you didn't mention the time frame for which it will recover, or the time frame in which it will
Okay,
recover.
okay. In that case, it took a little bit time because I would say that the battery system was immediate, of course, almost immediate. However, it was a couple of gensets that has, well, it was gas generators, because in Japan they use a lot this kind of gas generators, and for that case they was started the day after, because they had to repair, because of protections. One, it was the earthquake. For protection, they were just disabled, and you had to manually reconnect it. So the microgrid was immediately reconnected with battery. So it was working for one day using solar and battery with lower power. And then after one day, they reconnect the gas generators. So this means that we go into a stage in which, I don't know if I have it here. We go to a stage in which we have lower performances here, like this, right? So we go to a state in which we have lower performances, but still we have, we have enough power to support part of the loads. And then in the recovery stage, what we do is we restart. In that case was the day after the gensets, but still, of course, we don't go to 100% of performance because we don't have the grid there. So we are in island. It was just an example, let's say, but let's say that if you have, it will depend on what kind of disaster you have, what kind of, also how much time it will take for recovery, right?
Okay.
Will depend on the damages that you have. But in that case, it was like this. They were immediately going to this lower part, and then the recovery was the day after. I guess that it was only because that day was really a big chaos. So after some hours, they did realize that they have to restart the gas engines.
Okay. Thank you, Bijit. Ratna Rahul, if you please go ahead with your question.
Professor, regarding some small insights on related to artificial intelligence applications to microgrids.
Can you go again?
Yeah,
Please?
basically, he's asking, are there any research areas which are using artificial intelligence in DC microgrid? Do you see anything coming at the horizon, anything that will manifest into a big product which uses artificial intelligence?
Well, not directly. What I can see is that maybe a lot of things could be interesting with a little bit lower intelligence, like having MPC, so that you can, for instance, identify generation, identify storage, and you could maybe make kind of a, let's say, predictions. So it could be also in the prediction side. We did it. But if you think about having hardcore artificial intelligence, it's going to be very interesting, especially when you have a number of microgrid clusters interacting between them. I think that's going to be very interesting to look at that. Yeah.
One more thing, Professor, regarding are there any standards for cyber security attacks? Like if any cyber attack is there, are there any standards to be set for time of recovery?
Let's say that standards are as itself, I cannot see it right now, but I will say that cybersecurity is something that goes a little beyond. So cybersecurity, we have the cybersecurity in the level when someone tries to enter in the system, and we don't allow that hacker or this person with malicious intentions to the system. And this is one area of, let's say, computer science, very, very important. And the other is to say, okay, we accept that someone entered in the system and start doing things, and just observing how the microgrid is behaving, we can detect that really someone entered, and we can stop, let's say, this action. So this is something we are also working on it. And but right now I cannot see that there's a standard on that. I guess that it will take time to have really a standard.
Yeah.
Thank you.
Yeah,
Chetan,
thank you.
quickly go ahead, please.
Yeah, sir. Sir, what are the parameters which is mainly affecting the primary control? Like in
Sorry?
AC is different, in DC is different.
So,
Sir, what are the parameters?
Yeah, so he's basically asking what are the key parameters that afflict the primary control. Is that the question, Chetan? Yeah, I think, Prof, I think, are there any specific parameters that you look for which affect the primary control in a DC microgrid? I think that is the question.
Well, I think that differently than in an AC system, here we just have voltage and current. So with this we have to live, and that's good news on one side, because just we have one way of controlling the system, which is, for instance, we look at the current, we affect the voltage, or we look at the voltage, we affect the current. And I will say that from the primary level, it's kind of it's kind of an easy task, because I think it's very well developed today. So basically the parameter that in a DC microgrid affect us is, of course, if we have long distances between them, or let's say high impedances between the units, then you will have, let's say, impact, but sometimes this impact is also positive. Because, for instance, if you have a power converter which is very close to the load, it's logical that this power converter deliver more power to the load than another which is far away. So this is something that also will be helping, let's say, the physical distance of inside the microgrid. So this is something that has to be studied, and I think that this is amazing to see how sometimes something that could be against what we think that is logical, like having not a perfect power sharing between units, sometimes is good in terms of losses. So I will say that if we can think about how is the interaction of the primary control, and we go up to the tertiary control when we think about the optimization, I think it's going to be very, very nice topic also.
Okay. Thank you, Chetan. I had one last question, Prof. In the ferry, when you retrofitted the ferry, so what was the thought process? It was like, did you have to propose something? Were there any students involved? Like, how did it develop, that entire project?
Yeah, well, the project, we had our industrial partners. So you have to imagine that Danfoss is also in our university. And also the professor from Taiwan was with us half a year working here, and I was also going back. Okay. And then it was a number of students also working on that. As far as I remember, at least it was some PhD students and some also assistant professors working together with us. So yeah, it was really a teamwork, and I think it was very, very nice and successful.
Okay. Thank you, Prof. Thank you very much for your time. Thank you, everyone. We'll let the professor go. We thank him for his time and excellent presentation. Thank you for showing such practical work, Prof. And thank you very much for your time. We greatly appreciate it.
Yeah, thank you.
Thank you, Professor Srinath here.
Thank you, sir.
Bye-bye.